Can you see my presentation?
Yes, we can.
Yes,
Yes, we
yes.
can.
Okay. Well, I would like to start by thanking the organizer and thank you for inviting me and thank you for the introduction. Also, I would like to start by saying that I teach summer school. In fact, now I supposed to teach a class, but then I postpone my, the class till to start at 4 p.m. United Arab Emirate time. As you know, we have 1 hour difference. We are 1 hour ahead of you. So I want to apologize for my colleague in commutative ring. I love to be there, but maybe I will be there late to attend their talks. There are many good talks there. Okay, this is a general talk, and usually in my field, and I think all of us know, giving a general talk in abstract algebra is not always easy. So I hope this will work. Uh, from the title, my goal in this talk is to tell you why graph. I mean, why do we study graph and we connect the graph to rings? I mean, okay, give me a ring, I give you here is the graph. So what? That's a good question, and maybe many ask this question. So here I try to convince you that you can go back and forth between ring and graph. And I don't claim I am a graph theorist. In fact, I know some basic graph. I'm still learning about the graph because my research is in multiplicative ideal theory. But anyway, I try to make connection between ring structure and graph structure. Of course, this is a very huge field and is still expanding. In fact, it's not a secret. Myself and my colleague David Anderson, and there are 2 colleagues in India. We just submitted a book on graph from ring, and we have like 600 references in that book, and I'm sure we missed maybe more. So this subject is still expanding, and I cannot in 40 minutes tell you everything. I only want to tell you some of the basic thing on. Okay, so I already mentioned that. Yeah, here we need to observe that whenever I mention a ring, I mean the rings are commutative. Okay. Uh, Here is the definition of zero divisory graph. I know most of you know this definition, but again, this is not only for algebraists. This is a general talk, so I expect some of you maybe never seen this before. So what is the zero divisory graph of a ring? Of course, this is the notation I'm using here for the zero divisor graph. It's a symbolic graph. What symbolic graph mean? You don't, it's undirected and no multiple edges. And every graph consists of vertices and edges. So what will be the vertices of such a graph? It will be the set of all zero divisor take away 0. And how do we connect 2 vertices? If you multiply them, you get 0. Okay? So the vertices are the set of all non-zero zero divisors. That's the set of vertices. and how you connect by this condition here. Okay, here I mentioned some where, I mean, the first person, the first paper on the subject in 1988 by Buck or Beck. The name of the paper, Coloring of Commutative Ring, that appeared in Journal of Algebra. And in this paper, uh, Buck was uh, interested in coloring from the title of the vertices. In 1993, Anderson, D.D. Anderson, by the way, D.D. Anderson and D.F. Anderson, they are brothers, not just brothers, they are twin. And I think most of you know that. Uh, and both of them went to the University of Chicago, where they got their PhD. And to my knowledge, D.D. Anderson, he was a student of Kaplansky. Uh, David, I forgot the name of his advisor, really. Uh, anyway, 1988, the second paper I'm aware of came by D.D. Anderson and M. Nasir, and that's on the subject. And then in 1993, we have D.F. Anderson and his student Livingston. And that paper, if you go to Google search or Scholar, you will see that this paper cited more than maybe 1,500 times. Because this is really, I consider, the beginning of what we call now the zero divisor graph. Okay, so what are the things I wanna, here is it. As I told you, I wanna tell you some connection between graph and ring. Like, let's look at this result by Anderson and Lagrange. If you have a finite commutative ring, and the number of the vertices bigger or equal to 4, then your zero divisor graph is a star graph if and only if this. I mean, maybe this is easy result you're gonna tell me, but there is a connection. I mean, like I know the structure of the ring, if I know if and a star graph, you know what I mean with a star graph. Like I'm not sure if I never try that. If I can type here, like, uh, well, I'm not expert. I'm using tablet. I don't want to lose it. Uh, I think, let me try comment, maybe. Oh, I don't know. If some of you know, you can tell me how I can type on my PDF. I'm using tablet. Here maybe? No, but I should be able, I think. Anyway, a star graph, like you have one vertex connected to every, I mean, like let's call it A. And A is connected to every other vertex. Let's call them B1, B2, whatever. And none of the BIs are connected. So you have A connected to every BI by an edge, and none of the BIs are connected. This is what they call it a star graph. And if your graph and if you continue reading, if you have a starry graph of order p to the n, can be realized as the zero divisory graph of some ring. Okay, so here is a connection that every starry graph with p to the n vertices, it is the zero divisory graph of some ring. Okay, another definition, what in graph, they call it regular graph. What are the regular graph? When you have a connected graph and symbol, and the degrees uh, of the vertices are the same. So the degree of V1 is the same as the degree of V2, the same. All the vertices have the same degree. Some examples, like the complete bipartite. Complete bipartite is like, maybe here, K. Oh, I cannot do that. I don't know why. Anyway, complete bipartite, I think all of you know, mean like it look like the vertices are split into two sets, A and B. Every vertex in A is connected to every vertex in B, and every two vertices in A are not connected. Every two vertices in B are not connected. This is what complete bipartite. Complete bipartite mean the set of vertices split into two sets, one A and one B. Every vertex in A is connected to every vertex in B, and every two vertices in A are not connected. Every two vertices in B are not connected. And of course, you know, Km is regular, is complete graph. KNN is this mean complete bipartite. So your set A will have n vertices and your set B will have n vertices. Km is complete graph, and complete graph, all of us know, that means every two vertices connected by an edge. And of course, if you take a cycle, Cn, all these are example of regular graph. Okay? Here is a paper by Saeed Akbari. By the way, maybe I should mention most of the work on a graph done by Iranian mathematician. Uh, many papers on a graph were written by Iranian mathematician. Saeed Akbari, maybe some of you heard the name, and his colleague. Uh, Look at this result. If you have a commutative ring, then the zero divisory graph is regular, then it has to be either this or this. And this is kind of interesting because not all regular graph are complete, and not all regular graph are complete bipartite. So this is like kind of a nice connection in my views between the zero divisory graph and the regular graph. They are not okay. Then we go to the definition of what we mean with connected graph. Of course, all of you know what connected graph mean. Mean like you start from a vertex. If you have two vertices A and B, you should be able to go from A to B by a path. And we have to know the difference between a path and edge. An edge is one line segment, where a path is a sequence of line segment. So the graph is connected, and here be careful, I'm not saying an edge. It's a path. If between every two vertices there is a path, okay? And a path is a sequence of line segment. Like if you want to go from A to B, maybe you go from A to B1, B1 to B2, B2 to B3, and then B3 to B. So not directly by an edge. I mean, this is... Okay, what is the girth? The girth is defined to be the shortest cycle, the length of a shortest cycle. And what we mean with length? Length here, of course, we mean the number of the line segment in the cycle, or the number of the edges. And the same thing, uh, uh, okay, so the girth is the length of the shortest cycle. In that paper by Anderson and Livingston in 1999, these show that the girth has to be bigger or equal to 3. Of course, if there is no cycle, then the girth is infinity, just by, definition. Whenever we say the girth is infinity, that means the graph, and of course, if the graph is connected, that means it's a tree, because that's the definition of a tree. A tree is a connected graph with no cycle, okay? Anderson and Livingston, they show that if your graph, if the graph has a cycle, then the length, then the girth has to be between 3 and 7. They give example for 3 and 4, and they were not able to give examples for a graph with the girth 5, 6, or 7. And why? Because in 2002, Molay, S.B. Molay, in this paper, he showed that the girth 3, 4, infinity. It cannot be 5, cannot be 6, cannot be 7. So that will give a complete answer to the girth. Again, girth infinity means there is no cycle in the graph. Okay? Okay, here is another connection between structure of the ring and girth. If you assume your ring is reduced, reduced mean 0 is the only nilpotent element of the ring. And what do we mean with nilpotent element? X to the n equals 0 for some n bigger or equal 1. This is the definition of nilpotent element. So when you mention the ring is reduced, we mean that 0 is the only nilpotent element in the ring. So if your ring is reduced, then look, if you tell me the girth of the zero divisor is 4, then I know the structure of the ring. Here, the total quotient T here, be careful between this gamma, this is mean the zero divisor. T here is the total quotient ring. You know, the total quotient ring is like you localize R at the set of all non-zero, you remove if you let your S to be every element in R, take away the zero divisor, then the total quotient will be R localized at S. And of course, all of you know if R is integral domain, then this one here will be a field. Anyway, the total quotient ring of R has to be a product of two fields. Okay? And if you tell me the girth of the ring is 4, then I tell you what will be the zero divisory graph look like. The zero divisory graph look like complete bipartite with one set has M element and one set has N element. So you see the connection between a graph and the structure of the ring. There is not just here is the picture of the graph. There is something going on here. Okay, of course they have other result when the ring is not reduced. Here is a question. I mean, I don't know if this is like if the zero divisory graph is complete, will be the zero divisory graph of the polynomial ring complete? Remember, the complete mean you can, between every two vertices, there is a line segment, or between every two vertices, there is an edge, because an edge is a line segment. Okay? The answer is no, and here is the example. Well, if the answer is no for the polynomial ring, then definitely the answer is no for the power series. Okay? Okay, then the distance. What we mean with the distance between two vertices. The distance is the shortest path from X to Y. Like, what do I mean the shortest path? Like you can go from X to Y by crossing many edges. Like you can go from X to X1, X2, X3, X4, then you go to Y. And maybe you can go from X to X1 and then to Y. So the length of a path means the number of the line segment I use when I walk from X to Y. The shortest one, that's what we call it the distance between two vertices. Okay? And if you take the maximum, well, here I have to be careful. I take the supremum because supremum in analysis and maximum are different. But here I can use maximum. Why? Because it turns out that the diameter, and that's kind of interesting too, that the diameter of the zero divisory graph is either 1, 2, or 3. That's it. For any ring, the diameter. So the diameter of the graph is if you want to remove supremum and you write maximum, maximum of all the distances. So you calculate the distance between every two vertices. And remember, the distance means the length of the shortest path. And then you take the maximum number there. Okay, in 2006, locus, here is something missing. I told you, but I did not write it. I told you that the diameter will be 1 or 2 or 3. What that mean? That mean give me any ring, then in the zero divisory graph, I can walk from one vertex to another by crossing at most 3 vertices. I can always reach X to Y by crossing 3 the maxima. Well, I should not say that, but I should be able to do it by 3 edges or less. Okay? And this is kind of, I mean, when I saw that when I was young, I mean, like, I don't know what young mean, I thought this is kind of interesting. Because you would think at the beginning when you are not, when you see the proof, then you believe it. You think the distance can be anything, but it's not true. Okay, so if you are an algebraist and you know the diameter can be either, 1 or 2, 3, you start studying when like the diameter is 2 and when the diameter is 3. Here is a connection between ring structure and diameter. Look at this one. If R has more than 2 minimal prime ideal, and there are 2 zero divisors, A and B, where A plus B is not a zero divisor, then the diameter of the zero divisory graph is 3. Okay, so here is a connection between ring structure and diameter. If your ring is reduced and the zero divisor is not an ideal, then the diameter will be less or equal to 2 if and only if R has exactly 2 minimal prime ideal. If the zero divisor is not an ideal, and of course, if it's an ideal, he gave condition too. Just, cannot include everything. I'm trying to show you the connection between ring structure and a graph. So there is connection here. Okay, in 2014, I introduced a graph called Annihilatory Graph of a commutative ring. And what is this annihilatory graph? Annihilatory graph, again, it's simple, undirected, and the vertices, the same thing. The vertices are the set of non-zero zero divisor. And 2 distinct vertices are adjacent. Adjacent means, they are connected by an edge or line segment. If and only if the annihilator of xy not equal the annihilator of x union the annihilator of y. And another way to say that, the annihilator of x union annihilator of y is a proper subset of the annihilator of xy. Okay, so if you want to know again, if you want to follow this talk, the annihilatory graph, the set of vertices the same as the zero divisory graph. We still take the set of all non-zero zero divisor. And how we connect by this condition, the annihilator of xy, and of course you know what the annihilator mean. Annihilator of xy, you're looking for the elements, let's see b in R, where bxy equals 0. The same thing, what's the annihilator of x? You're looking for the elements in R that kill x. And the same thing for y. Okay, so let's look at, well, property of this graph. This graph is like, I don't know what, the diameter even cannot be 3. It's connected with diameter less or equal to 2. And if you look at number 2, if your ring is reduced, then the annihilatory graph is the same as the zero divisory graph if and only if R has exactly 2 distinct minimal prime ideal. If your ring has exactly 2 distinct minimal prime ideal and the ring is reduced, then definitely these 2 graphs are the same. Okay? What about number 4? If non-reduced, you know what that means. The opposite of reduced. That means there exists at least one nilpotent element that is not zero, where nil is the set of all nilpotent elements. If non-reduced and the nil of R square is not zero, then these two graphs are not the same. The zero divisory graph is not the same as the annihilator, and the girth has to be 3. If you have non-reduced and the zero divisor is not an ideal, then the annihilator graph is not the same as the zero divisor. I mean, this is trivial for number 2. Number 2, look at the example. R here is reduced. Clearly, R has 3 minimally prime ideal. So definitely the zero divisory graph will not be the same as the annihilatory graph. Okay, here is something kind of interesting. Uh, 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 there is in 2007, I introduced a concept called two absorbing ideal. And a proper ideal is called two absorbing if whenever you have ABC in R and ABC in I, then AB in I or AC in I or BC in I. This is like generalization of a prime ideal. Like we call a prime ideal, if you want, you can call it one absorbing. Because in a prime ideal, you have A, B, and I, and you want A in I or B in I. Here we take like 3 things in I, and we want 2 of them to be in I. Okay, this is a different subject, but why did I mention that? I don't know, mathematician, we are connected by spirit or what. Look at the previous result. Here I have like many conditions where whether they are equal or not equal and whether the ring reduced or non-reduced. Iranian mathematician here, I cannot even, Bayrovi and Babai, in this paper here, look what the answer. Let R be a commutative ring. That's it. Not reduced. Then these two graphs are the same if and only if 0 is two absorbing ideal. So the annihilatory graph is the same as the zero divisory graph if and only if 0 is a two absorbing ideal. Uh, I like this result because, like in my previous, I gave like many conditions when they are equal and when they are not equal. And I have to split that into reduced and non-reduced. But here, like a complete answer using the concept of two absorbing. Okay, here is another connection for between a graph, like assume that the annihilatory graph is not the same as the zero divisory graph. Then if you tell me the girth of the annihilator is 4, then I can tell you what is the ring structure. Okay? And the other way around, So the girth of the annihilatory graph is 4 under this assumption. Then I know quickly how the ring look like. All right. And here, the same thing. Here, non-reduced ring, the only condition non-reduced. If you tell me the girth of the annihilator 4, then I can tell you what is the structure of the ring. It seems they are the same result I'm giving here. No, I added that these two are not equal. But here, if non-reduced, girth 4 mean that. Okay, anyway. And also, look, I know how the annihilatory graph look like. K2, 3. Wow. Okay. Okay. How many minutes left for me?
You have around 30. Wait, hold on. Let me just check. 30 minutes?
13?
No. Sorry, 23 minutes.
Oh, okay. Another graph. So we studied a zero divisory graph, annihilatory graph. Here is another one called total graph. And that was introduced by Anderson and myself in 2008. And what is the total graph? And here's the notation. T for total. And this is, just notation. So the whole thing here mean the total equation, the total graph. The same thing is symbol graph, but here the set of vertices, all the elements of R, all elements of R is the set of all vertices, and if you have two distinct vertices, we connect them if they are adjacent, meaning they are connected by an edge. If and only if, when you add them, you get a zero divisor. So I'm allowing 0 here in ZR. ZR is the set of all zero divisor. So what the total graph mean? Your vertices is the set of all elements of the ring, and how you connect two vertices or two elements. When you add them, you come up with a zero divisor. A subgraph is regular. R for regular is a subgraph of the total. What are the vertices? From the name, the vertices of the regular total graph is the set, the element of R, take away the zero divisor of R. So pay attention to this. The regular total graph, the set of vertices will be only the regular element, meaning all elements in R except the zero element. Okay, here is some structure. Like if you have a commutative ring and assume the zero divisor is an ideal, and assume the cardinality of the zero divisor is alpha, the cardinality of R mod the zero divisor is beta, then I know the structure of the regular graph. If it depends on 2, if 2 is a zero divisor, then I know that the regular graph is going to be the union of beta minus 1 disjoint K alpha. K alpha here, complete graph, and remember alpha is the cardinality of the zero divisor. If 2 is not a zero divisor, then the regular graph is the union of that. Okay, and then if you look at this result, like when is the regular graph complete? Complete answer. Regular graph, remember regular graph mean the set of vertices, all elements of R except the zero divisor, and how you connect if you have A and B, A and B, both of them are they are not zero divisor. When you add them, you should come up with a zero divisor. So the regular graph is complete if and only if R mod 0 isomorphic to Z2 or Z3. And here's another connection between ring structure and this graph. Regular graph is connected if and only if R mod Z2 mod the zero divisor of R, or Z2, or R mod the zero divisor of R Z3. I mean isomorphic. Okay? And then the regular graph is totally disconnected if and only if R is an integral domain with characteristic equal to. Okay. Here is another property on ring and graph. Regular graph is connected means either x plus y is a zero divisor or x minus y is a zero divisor for every xy for every xy regular R. Regular R mean the set of all elements of R, take away the zero divisor. Okay? And you can read that. All right, here is something different. Remember that in the annihilatory graph and in the zero divisory graph, and in fact, there are many other graphs. Many of these graphs, diameter always between 1, 2, 3, you know, uh, most of them, they have this diameter. In the total graph, the diameter can be any number. Later on, you're going to see, give me a number n. I will be able to give you a ring R where the diameter of the total graph of that ring is the given n. So this is completely, I mean, this is kind of different from the zero divisory graph and annihilatory graph. And in fact, if you read this theorem, it tells you how to construct the diameter. Let R be a commutative ring with the zero of R not an ideal. Okay, by the way, maybe I did not mention that earlier. If the zero divisor of R is an ideal, then your graph will never be connected. Your graph will consist of component. If the zero divisor of R is an ideal, the total graph will never be connected. It will be consist of components. Some of these components will be complete, and some of these components will be complete bipartite. So if you're looking for a connected graph, the zero divisor should not be an ideal, like here. Then the totally connected if and only if you can write 1 as a sum of zero divisor, z1 up to zn, where z1, zn are zero divisors. And if you let n be the least integer, n is the least integer where you can write 1 as a sum, that will be the diameter. Okay, quickly, if your ring is finite commutative ring and the zero divisor is not an ideal, then definitely the total graph will be connected and the diameter is 2, right? And the proof of that is clear, right? Because if you have a finite commutative ring, you know the structure, and you can you will have idempotent there, uh, and you know like E and 1 minus E, and if you add them, you get 1 in a finite commutative where the zero divisor is not an ideal. Be careful. So I'm avoiding field and quasi-local. Well, that's a field anyway. Okay. Uh, okay, here is to find the diameter of the total graph is enough to know the distance between 0 and 1. So the diameter of the graph of the diameter of the total graph of the ring is equal to the distance between 0 and 1. If the diameter of the total graph is n, remember the total graph, the vertices is the set of all elements of R, where the regular graph, the set of vertices is R, take away the zero divisor. If the diameter is n, then the diameter of the regular is bigger or equal to n minus 2. In this paper by Saeed Akbari, they are also Iranian mathematician, uh, these show that if R is commutative Noetherian ring and the diameter of the total graph is n, then the diameter of the regular has to be between n minus 2 and n, between these two. And of course, in that paper, they give example where the diameter of the regular graph bigger than n minus 2 and diameter of the regular graph strictly less than n. So these show there are numbers between n minus 2 and n. Okay? And here is the question I told you. In the following example, for every integer n, we construct a commutative ring such that the zero divisor of Rn is not an ideal and the total graph is connected and the diameter is the given n. I'll let you stare at this. This has to do with ideal, what you call it, a trivial extension, or I call it idealization, a ring with M, where M is an R modulo. This is very, I mean, technical how you start. You start building these ideals, P0, then you build Bi, sorry, and you know you start doing. But they, I mean, these things, if you are interested, they are in the paper. You can get, you know, the detail of this example here. And here is my ring. Rn will be that. Okay, this is like is not trivial and it's not. I mean, what I call it technical. Like you really need uh, to choose your ideals carefully, and then you come up with the ring. I mean, this ring here, the total graph of this ring, the diameter is going to be n. Okay. The last thing I want to entertain you with, this is a recent work, uh, myself with my colleague Rosie Risner, Ramsey number. Because whenever you study graph, you come up through Ramsey number. Here we study Ramsey number for partial order graph. So the last one I want to share with you, what is partial order graph? And here you have like a simple undirected graph with vertex set A. And so you start with a set A and you define a partial order on A. Okay? So your set of vertices will be like partially ordered. And then partial order graph is simple and directed, and two vertices, of course distinct, are connected by a line segment if A less or equal to B or B less or equal to A. Of course, less or equal depends on what the definition of the partial order. Okay? And here is the question we try to answer. If you have a class of, here we, to make it easy quickly, consider C be the set of all partial order graph, all. And we want to calculate the Ramsey number. Like you put some number here, like 2, 4, or 5, 6. So what's the Ramsey number mean? Mean the minimum number of vertices are such that every induced subgraph of an arbitrary partial order graph consisting of R vertices contains either a complete subgraph Kn or independent set. Independent set meaning every two vertices are not connected by an edge. So like when you tell me I have a set of order, independent set of order 7, then I know every two vertices in this set, every two not connected by an edge. Okay? So to make it simple, the Ramsey number mean I'm looking at the set of all partial order graph, and I want to find the smallest number of vertices R I can select. So either the subgraph I selected will have either Kn as a subgraph, or it has M, a set with M independent element. Okay? Anyway, we were able to have a formula for this partial order graph. Like let n, then the Ramsey number with respect to the class C of partial order graph satisfy this. Remember here we are considering C is the set of all, and of course here is something missing, RCNM. There is NM. Anyway, this is also, if you are interested, you can read it. What are the implication of this theorem? Here is the implication. I give you some example. Like let Mn be positive integer. And what is the smallest number of student in a class A where at least M student, give them name S1 to Sm, we have the age of S1 strictly less than the age of S2, strictly, well, here I change capital S to small, but you know how to follow. Or there are at least any student, B1, Bn, where the age of B1 equal. Like you enter a classroom, you don't know nothing, randomly, and you choose a number like 5, 4. You want to make a statement, and you're going to say there is at least 5 students where the age of the student 1 less than the age of student 2, and so on till you reach the age of student 5. Or there are, what are the other number I selected? Maybe 4. At least 4 where, call them B1, B4, where the age of the first boy equal the age of the second till you reach the age of B4. Such number, the smallest, is m minus 1 times n minus 1 plus 1 for the answer to this question. And remember here is, okay, here is something has to do with ideals. Here I said left ideal or right ideal. No, idempotent. Like if you have your ring and you choose a set from your ring where the cardinality of this set A is bigger than or equal to K, then you should be able to find n element where A1 divide A2 divide A, keep going, or there are m distinct element where none of these numbers divide the other. Okay, and then this is the last, and I'm done. Like if you have a ring and you choose S to be the set of ideal of, if the ring is commutative, you just remove left. But in general here, this is an example where R need not be commutative. If you choose S to be the set of ideals where I is non-trivial left ideal, and the number of the elements in this set is bigger or equal to this number, then one of these two statements must be true. What are they? You should be able to find a chain of ideals, and here look, here not equal. I1 is like a proper subset of I2 up to In, or you should be able to find M left ideal where none of the ideals here contained in the other. Okay? Anyway, and the last one, if you want to ask your student this question, let Mn be positive integer. Let R be the smallest positive integer such that there are at least m positive integer S1 up to Sm such that S1 divide S2 divide, keep going, or there are at least n positive integer where Bi is not a factor of Bk for every Ik where I not equal to k and I and k between 1 and n. What is this smallest number you should choose to make sure that the first statement is correct or the second? The answer is this, m minus 1 times n minus 1 plus 1. And I thank you very much, and I finish.
Thank you, Professor Badawi, for this interesting talk. Let's applaud the speaker. So if you can unmute yourself.
Thank you.
So the floor is open for questions. And maybe I can start off with one question.
Yes, thank you, Professor Badawi, for the interesting talk. Is there any way to classify when the relationship between the annihilator graph and the zero graph? I mean, one of them as a subgraph of the other one?
Thank you. Thank you very much. Thank you for the invitation, and it's good to see all of you.
Thank you. Abdullah, are you with us?
Yes, I'm with you. As we reach the end of the second day of the conference with 3 nice talks in pure mathematics, it was really nice to see the recent results and the connection between geometry and algebraic topology, between geometry and dynamical system, and lastly, with Professor Badawi, commutative algebra with the graph theory. I'm sure this will encourage our faculty members as well as our graduate students to look more into these directions in the future. On behalf of everyone, Professor Botvinnik, Professor Zoraib, and Professor Badawi, I would like to thank you for your participation in the conference today. We are grateful for the time and the effort you took to share your research, thoughts, and expertise with us. It was critical to the success of this event. I think now it's a good time to take a group picture. So I would like to encourage everyone to turn on your camera, please, and we will take a group picture.